section 2.1, and this is just the very beginnings of calculus. And what I think is so neat about calculus is that a big portion of it is just getting any graph, zooming into any graph to see that it's really just a line. If you get close enough into any part of a graph, you can just see a straight line, right? And you can talk about the rate of change, the slope of that line, right? And these are skills, these are ideas that we learned actually in Algebra 1, right? We learned how to write the equation for a line. And so what we're going to be doing in calculus a lot, you're going to discover, is writing the equation for a line. Do you remember what you need to write the equation for a line? Excellent. You need a point and a slope, right? And so far you've learned that you could find the slope a couple of different ways. Like if you had 2 points, you could count it, or if you were told the two lines were parallel, you could look at the other line and find the slope. You know, you had some information about how to find the slope, but you needed the slope. Well, what you're going to learn in calculus is that the derivative of a function actually gives you the slope. And so if you're given a function and you find its derivative and you plug in a point, you can get a slope. And then you had the point, and then you write the equation for line. It's called the equation of the tangent line. So that's where we'll be heading in this section, but really all the way through calculus, getting it down to the very, very small is where we're headed. Hi. Do you want to get? Are you from Robinson? Or are you? No, you're here. And what's your name?
Alex.
Alex. What's your last
Barnett.
name? Barnett. Okay. Not on this roll yet. I probably haven't. Did you just enroll recently? Oh. This is an old one. What's your major, Alex? Exciting. We have a program now, so we get students. All right. There's big money in engineering. All right, so let's go ahead and start section 2.1. So I'm going to hit this button. All right, so let me make that fit on the screen a little bit better. I think I can make this shrink. I can do that. How's that? Okay, that looks pretty good. Okay, so the first thing you're asked to do is to define average rate of change of a function and interpret this graphically. Okay, so the average rate of change over an interval and, you know, in math, we like to put letters in just to make it generic, right? So our interval will be from x sub 1 to x sub 2. So 2 to 3, 7 to 5, that makes sense, 7 to 9, just over some interval, -4 to 6, is, all right, guess what? The average rate of change is just the slope over a particular interval. And so, okay, so actually, the average rate of change of a function f of x, over an interval from x1 to x1 to x2 is the change in y over the change in x. And so in function notation, the y coordinate at x2 is what? Well, if our function is f of x, the y coordinate at x2 would be f of x sub 2. Okay, so it's just notation, but this is like whatever this x sub 2 is, you would plug it into the function and you would get the corresponding y value. So this is f of x sub 2 minus f of x sub 1. And we're going to divide that by the length of the interval or the change in x. So this is going to be x sub 2 minus x sub 1. Right? And so, the button I want. Okay, and so graphically, it's just if you have a function, say here, this is x, and this is y, which is your f of x, and you just pop in a function anywhere in here. So we could just say maybe something like that. If this is x sub 1 and this is x sub 2, then you come up here to find the corresponding y value, and you would plug it into the function, and then this over here would be f of x sub 1, and then you come up here, take that corresponding, take that x sub 2, and then you would get what the y value is. That would be the function at x sub 2. Right, this is all just scary notation. But the sooner you get more comfortable with it, the better. All right, and so then the f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1 would then be just your average rate of change, or if we were to draw a line between these two, it would be the slope of that line, and that is called the secant line. You remember secant lines are lines that intersect. I don't know if from geometry you remember a secant line intersects a circle in two places, and the tangent line just barely touches the circle in one place, right? So the idea with calculus that we're going to get to is that we're going to get x1 and x2 very, 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 very close to each other. We're going to make the distance between them become smaller and smaller, and when that happens, these 2 points get almost on top of each other, right? And you make the secant line become a tangent line, right? Just by squishing them closer and closer together. And that tangent line, then we would call that the slope of the tangent line for a particular point. Okay, but we can start just right here. So this is the slope of the secant line. Did you get are you from Robinson, or are you here? You're just here. And what's your name? Kyle. Okay. What's your last name, Kyle?
Ganaway.
Say it again?
Ganaway.
Okay. What's your major, Kyle? Good. All right, well, everybody here is doing engineering, or you got education, computer science. Pick one of those.
Physics.
Physics is a good one, too. You have a great physics instructor. Okay, so let's do a little example where we're going to find, my function looks kind of chopped off. That's x cubed plus 1, and we want to find the average rate of change of x cubed plus 1 over some certain interval. Okay, so this isn't going to be too bad. We'll need to figure out, this of course is going to be my x sub 1, and this will be my x sub 2. So I'll just do f of 3, because that's x sub 2, minus f of 2 over the interval x2 minus x1, so 3 minus 2. Everybody okay? All right, so what is f of 3? Well, what that means is you're going to plug 3 in for x in your function. So 3 cubed is 27 plus 1 is 28 minus f of 2, you plug 2 in for x in your function. 2 cubed is 8 plus 1 is 9. And you divide by 3 minus 2, which is 1. Everyone okay? All right, and 28 minus 9 then is 19 over 1, or just 19. Okay, and then if we want to do the second one, we would do f of 1 minus f of negative 1 over 1 minus negative 1. Okay, and so who wants to tell me what f of 1 is? 2, right? You plug 1 into the function. 1 cubed is 1 plus 1 is 2. And then f at negative 1 is 0, because negative 1 cubed is actually negative 1, right? And then plus 1 is negative 1, so this is going to be minus 0 over, be careful here, you got your slash and dash. Has it been a while since y'all been doing any math? I don't know. Anyway, that's 2. because we have 1 plus 1 is 2, and so 2 over 2 is then 1. So we have a slope of 1 over the interval from -1 to +1. Okay? And so just for grins, let's look at what that looks like visually on your calculator. Everybody say a prayer to the calculator God, because mine, sometimes it like just not work, but it seems to be working right at the moment. So thank you for your respect. Okay, for some reason that went away. Okay, so we will do, if you looked at the graph, so if I just go to y equals here and I type in the graph x cubed plus 1, I'll do the x, which is to the right of the alpha, and we can raise it to the third power with the little hat right there, and then plus 1. And then if we go, probably just zoom 6, it's been a while. Yeah, zoom 6 is the standard viewing window, and we'll just see our friend, the cubic function, right? And then you will see, if you were to look at the interval, I don't know if it'll let me. Yeah, I know what I'll do. See here. If you were to look at the interval, let me grab this, from 2 to 3, so here's 2 and here's 3. This slope, what they're saying right there, that slope is 19. The average rate of change is 19. But if you look at the slope from -1 to 1, so between here and here, you notice that it's not nearly as steep. Do y'all see that? So its average rate of change there is 1. Okay? So just that's all you're looking at. Kind of fun. And I got to be cool with all of my technology there, so be impressed with how cool I am. All right, how about we do a trig function, because life is not, that's why you're not in business calculus, right? Business calculus, you get to skip the trig. Regular calculus, you get to do the trig, and you love the trig. Okay, so now we have an H instead of an F, but we're not going to worry about that. And we have T's instead of X's, but we're not going to worry about that either, because this is math, and we don't care about letters in math. Okay, so your average rate of change, which is really just your slope, is going to be H of the second coordinate, which is 3 pi over 4, minus H of the first coordinate, which is pi over 4, divided by the length of the interval, and this is a typo, 3 pi over 4 minus pi over 4. And you're breathing. Okay, and so say you're a little freaked out because you haven't thought about calculus, or you haven't thought about trig in a while, and maybe the unit circle is not your friend as it should be. And so if you have that feeling, then what I would encourage you to do is go to your website, and there should be, there isn't yet, but I promise, under the lessons button very soon, there will be an additional resources button. I will add it, and it will have a unit circle that you will like. It'll have a trig sheet. So I'll put that trig formula sheet. I've forgotten to put it up yet. Yeah.
Will you be able to use that sheet?
Well, I didn't talk to you guys about the tests or the homework, but everything is online. So the tests will be online, and they will be taken at your convenience. So yes, what you have in front of you will be whatever you have in front of you. What you can't have in front of you is, your math teacher from high school or someone that's really good at math. But if you have things in front of you to work, that's fine. And you will turn in your work to me that you do, but it'll all be kind of take home. So yeah, you can have that with you. But I don't know, if you don't have your unit circle memorized, you're really not very cool. And I know that that's important to you, to be cool, and that's why you're taking calculus. Okay, but anyway, the quarters are fun, right? The quarter pies, 3 pi over 4, 5 pi over 4, 7 pi over 4, they were fun because the sine and the cosine were the same value, right? And that value was 1 divided by the square root of 2 or square root of 2 over 2. And it depended what quadrant you are, whether they were positive or negative, right? But for example, 3 pi over 4, if 180 degrees is halfway around the unit circle, right? That's pi. So 3/4 of a pi is actually in the second quadrant. And in the second quadrant, your x is negative, your y is positive, right? So it's negative square root of 2 over 2 and positive square root of 2 over 2. And remember, it's cosine and then sine. Now, the cotangent is the cosine over the sine. So you will just do negative square root of 2 over 2 over square root of 2 over 2, all of that work to get -1, right? Yeah. And then, if you put pi over 4 in, pi over 4 is 45 degrees, right? First quadrant, the happy quadrant, everything's positive. The sine of pi over 4 is square root of 2 over 2. The cosine of pi over 4 is square root of 2 over 2. You divide them, because that's cotangent, you divide cosine over sine. It's still going to be 1 because they're the same there, right? Okay, of course, if you're having a bad day, you can change your mode in your calculator. Make sure you're in radian mode. And then you can just type in the cotangent. You have to do a little bit of work here. You have to do 1 divided by the tangent of 3 pi divided by 4, and it will tell you -1, which you would do just to check yourself, not to actually cheat with, right? Whatever, I don't care. I'm not teaching trig. 3 pi over 4 minus pi over 4. 3/4 minus 1/4 is 2/4 or 1/2. And so this is pi over 2. Oh my gosh. And so -1 minus 1 is -2 over pi over 2. So this we just, of course, write horizontally. So this is -2 over 1 times 2 over pi. So finally, our answer is -4 over pi, which I'm sure was what you were thinking was the answer to that problem. Okay? So yeah, just a lot of math review there, a lot of algebra, but this is calculus, so right? Now, just a lot of, little bit of review. It feels hard to do in August. Okay, so let's look at this problem. It says, I wonder if I just reduce this a little bit. We'll see the picture. That's better. Okay, it says, the profits of a small company for each of the first 5 years of its operation are given in the following table. Plot the points representing the profit as a function of year and join them by as smooth a curve as you can. Okay, so it looks like we've got, I'm just going to let t equal 0 be 1990. And then I'm just going to count by ones. So then we have 1, 2, 3, 4. And then it looks like I need to get to 174. So I will count by maybe 20s. 20, 40, 60, 80, 100, 120, 140, 160, 180. In these days of technology, a little Excel might go a long way as far as graphing this, but I'm just doing it by hand to just give us a little bit of a sense. Okay, so in year 0, we were at 6, so maybe about there. In year 1, 1991, we were at 27. In year 2, we were at 62. In year 3, we were at 111. And in year 4, we were at 174. And so we have sort of a maybe hopefully slightly bending up curve. Okay? And so this is profit in thousands. And this is the year since 1990. Okay, and then we were asked now, what is the average rate of increase of profits between 1992 and 1994? So average rate of change, you're just going to do the change from 1994 to from 1992 to 1994. So you're going to find that difference, and then you're going to divide by the change in the years. And so that's going to be 174. Let me make sure. Yeah, 174 minus. In 1992, it was 62 divided by 1994 minus 1992, which is 112 divided by 2, or 56. And so what this means in the context of the problem is that we have an increase of $56,000 per year. Okay. All right, it says use your graph to estimate the rate at which the profits were changing in 1992. Okay, and so what you would do if you wanted to know at the moment of 1992, you would want to go on either side of 1992 and make an estimate. So you could just look at the rate of change between 1991 and 1993. There's kind of lots of ways that you could approach this. And you see that if you were to find that slope, it would be about what the rate of change is in 1992. To see, it sort of looks pretty close to that change. So now the idea here is that we could look mid-year between 1991 and 1992. So maybe in June, and then also in June between 1992 and 1993. And that interval then would be shorter, and so our estimate of the rate of change would be better. Right? And then we would come in even closer. And so we would be trying to shrink our interval around 1992, which would give us a better and better estimate of the rate of change in that time period. Does that make sense? So that's the whole idea of calculus, to look at the infinitely small, where the distance between those 2 points is infinitely small, and then also the infinitely large. But we're not talking about that just right now. But that's the calculus is kind of putting infinity into our thought process. Okay, so one estimate would be just to use, since we only have the numbers for 1993 and 1991, we could use those numbers. So we could do 111 minus 27 over 1993 minus 1991. And so 111 minus 27 is 84 over 2, which is 42. So 42,000 is the rate of increase in 1992. Okay? And so this part C leads us to the first main concept in calculus, is what we call the instantaneous rate of change. If you make that interval small enough, you can figure out what is happening at a particular instant. And so from an engineering and a physics perspective, a lot of times when you are observing a projectile or you observing a planet's motion in space, what you can actually see is what's happening at the instant. You want to get back to describe the path of that object, right? So you actually have to use what we call integral calculus in order to do that. You have to go from the rate of change back to the function, okay? Whereas right now we have the function and we're going to the rate of change. But you always do that in math, don't you? You do it and then you undo it. You added, then you subtracted, you multiplied, you divided, you squared, you square root. So in this class also, we will differentiate first and then we will integrate. But in your engineering and in your physics classes, a lot of times you have the problem that you have the motion, or you have the let's see, you have the motion and you want, like you have the velocity and you want to get back to the position. You want to describe it that way. So it's called integral calculus. Okay, so an informal definition, and this, you may not find this that informal, but it is sort of informal for as far as math goes. Math can be very formal. We can use lots of letters and Greek letters mixed with Latin letters, and we can get very sophisticated. So this would be what I consider somewhat informal. An informal definition of a limit is we will let, we always start with that word, f of x, so that's my function, be defined, which means that it has a value for every point in the domain of this interval that I'm going to give it. So it's defined on an open interval. When we say open, because we're not going to worry about what happens at the endpoints right now. And so an open interval about x naught. Okay, so that might be kind of scary language right there. X sub 0 is x naught. You might hear me say x naught, all for naught. What happens at time 0, your initial point. P naught, you may have heard in physics, is your initial position, right? H naught is your initial height. V naught is your initial velocity, NAUGHT. Okay, so it's defined on an open interval about x naught. So you're capturing x naught on either side of it. X naught's in the middle, and you're putting your piece in between. So like 1992 was in the middle, and you had 1991 and 1993 on either side of it. So 1991 to 1993 was like our interval, and 1992 was like our x naught. That was our about. Okay? And just to be more confusing, we're going to say except possibly at x naught itself. So what we're saying there is, all right, if the function is not defined at x naught, exactly x naught, but it is everywhere else, we can still say what the limit is. Okay, this is we're just adding a little bit of complication there. So if f of x gets arbitrarily close to some y value, and we'll call that y value, I don't know, how about big L for limit? And it turns out we can get as close to L as we like. Right, so like if it's hard at the year one, but if we did June of 1991 and then July of 1991 and August of 1991, we were getting closer and closer to 1992. We were getting closer and closer to what the actual value was in 1992, the y value, because it's smooth and continuous, right? Okay. So as close as we want, we can get to this y value for all. Okay, so let's see. If f of x gets arbitrarily close to some y value called L for all x, really close to x naught, so we're just trying to get as close as we want, we say that f approaches the limit L as x approaches x naught. And we write the limit as x approaches x naught, and it's almost like you see me say, as I write it, I'm saying it. The limit as x approaches x naught, the little arrow goes for approach, of f of x, there's my function, is equal to what? What is it equal to? It's equal to L. That's the y value. Okay? So this is your first experience maybe with limit notation. So this is the y value as you get close to x naught. And it's as close as you want. All right? And you keep getting closer and closer, like really, really close, and really, really, really close, and really, really, really close. And you're always hitting on this number, you know, like you get to 19, and 19.01, and 19.001, and you're really hitting on 19. So you have a sense that that's the limit's value. Yeah.
So is this like the non-existent point that is never passed?
Yeah, it's like, yeah. Well, because, right, you're not going to go beyond x naught, but you can actually come into x naught from the left or the right.
Yeah. That's where you have the graphs like this.
Right. But it can be a graph. Well, at that, if you have a graph that goes like, and people can't see. If you had a graph that went like this, and you were looking at the point right there where it had, like, that's called a vertical asymptote, we would say that the limit actually doesn't exist there, because that graph would be going to infinity, and you would never be able to actually get a number.
Okay.
What we're more interested in is a smooth graph like that, and maybe at that one point right there, what is the y value? Well, I can come in this way or come in that way, but I'm always going to get closer and closer to the actual y value. Or you could have a little hole in the graph. And so from the left and the right, you get to the same value, but at that point, you have a hole. That's still okay. You still have a limit. Okay. But what you're talking about, when you have asymptotes, the limit doesn't really exist. Sometimes some books will say that the limit is infinite, but that kind of backs off from the definition of a limit, which is that you should be able to actually get a number. Okay. Does that make sense?
So this isn't talking about horizontal vertical.
Not yet.
This is just talking about before you reach.
Right, on either side of it, yeah. Yeah, but you do talk about limits with regards to asymptotes, but we're just not quite there yet. Okay. Okay, and so let's look at it from a graphical perspective. What is the limit, and this is I just copied and pasted this from your book, so it's kind of hard to read, but this is asking for the limit as t approaches -2 of f of t. Oh, sorry. F of t. That's the first one. All right? So what you're going to do is you're going to look at your graph and you're going to approach, this is really saying, what is the y value as my x value approaches -2? Okay? Well, in order for the limit to exist, you have to get the same y value from the left and from the right. Okay? So as I'm traveling from the left of -2, and I'm looking at corresponding y values. So I'm coming in this way, and I'm looking at the corresponding y values. What kind of y values am I getting? What is the y value? What does it seem to be getting closer and closer to? Good. The y value seems to be coming into 0. And the same thing here. At -1, I get -1, but as I get closer to -2, my y value, if I come over here, I can see it's getting closer and closer to 0, right? So the limit as t approaches -2 of f of t is, in fact, 0. Now, B asks for the limit as t approaches -1. Okay, so let's look at that. -1, if I come in from the left, what's the y value that I'm getting closer and closer to? -1. And if I come in from the right, notice I always am getting -1, right? And so it is, in fact, -1. So say to yourself, what is the y value as the t or the x comes in from either side? All right? How about the limit as t goes to 0 of f of t? Well, did you say d/e? Does not exist. You are correct. And the reason it doesn't exist is because, remember, this is the x value, or in this case, the t. If I come in to 0 from the right, I'm always getting a y value of 1, except at the moment that it's 0 where it jumps to 0, right? It's okay that I'm coming in, that the limit does not exist at 0. The problem is that when I come in from the left, I'm at -1. So I have this jump. Do you see what I'm saying? See, at -2, it didn't matter that the function didn't exist at -2, that there was this open circle. Because I came in from the left and from the right, and on either side I was getting 0, that's how I could say that the limit was 0. But at t equals 0, if I come in from the right, I get a y value of 1. If I come in from the left, I get a y value as -1. And that's my problem, right? Okay, so this one does not exist because I do not get the same value from the left and the right. Yeah?
So that goes for all y. They're not the same. The limit does not exist.
The limit does not exist. Now, we're not going to do this in this section, but I could say what is the limit as t approaches 0 from the right. I put a little plus sign there. And if I had done that, then that limit is in fact 1. As I approach from the right, I'm always getting a y value of 1. And the same logic, the limit as t approaches 0 from the left, that is in fact -1. But the limit as t approaches 0, because these two do not match, does not exist. Okay? All right, let's look at another one. We can use our calculator to help us work this one. We go to y equals, and when you're typing in a polynomial like this, you're going to want to put the numerator and the denominator in parentheses. So I'll put a parenthesis here, and I'll have x plus 6, and then divided by, and then I do another parenthesis, x squared plus 4x minus 12, and close that parenthesis. Are you with me? All right, and then I can go to the table on my calculator, which is the second function for the graph button. It says table, so I'll do second table. And I can go up here and I can go up into the, or I can just hit delete, and I can delete out the different parts. Does anybody have a calculator and their table is not set up to do that? Is everybody's table working that way? Yeah, okay. If your table wasn't working, you can go to second table setup, and you always want the independent variable to be on ask, and that'll allow you to type stuff in. If you put it on auto, it just will automatically fill in that x values based on what you put as your increment. Okay, so if I go to table, oops, I hit graph. And now I put in these different x values, negative 5.9. Negative 5.99, negative 5.999. What do you notice about the y values? Well, they seem to be, if I actually get on it, I can see more decimals down here. They seem to be getting very close to a particular number, don't they? Negative 0.125. Maybe. Let's see if I come in to the other side of negative 6. To the left of negative 6 would be like negative 6.1. A little bit closer, but still to the left would be negative 6.01. And even closer would be negative 6.001. And so it does appear that as I come in from the left or the right, the y value is negative 0.125. Does that make sense? Okay. And so we would say that this limit from our calculator and let me grab that. Okay. Not very big. Okay, so if you looked at the graph on your calculator, and what you would do is we would just zoom into negative 6. So one thing to do, this is kind of fun, if you hit the zoom button and then you have some choices here. The zoom box is kind of fun, that first one. And what you want to do is move your cursor to where you're about at -6. See, my x is right there at -4. And if I hit enter, then I think it'll start to draw a box. And I can go up and over, you know, like that. I think this will work. Let's see. Then it should, I don't actually have that much experience doing this. Let's see. Yeah. I'm not very good. Just kidding. I'm not very good at the zoom box. Let me try. Zoom. I'm just going to do zoom 6. And then I'm going to do a zoom. What I do, this is what I would do. I just would do like, since I want to be near -6, I would do like from -7 to -5. And it was clear that I was really hugging the y-axis there, the x-axis. So I would make this like -1 to 1 on the y. Yeah, thank you. I'll fix that in just a second. So -7 to -5. And then if I were to trace, and then notice there is a hole at -6. Do you see how the graph is not defined at -6? But if I hit the trace and I get really close, I can see -1.24. See, and if I go this way, -6 is not defined, but if I go on the other side, I'm at the -1.25. Okay, so it does appear that on either side of -6, I do get 0.125. Okay, now, on either side, approaching -0.125. But notice at the instant of -6, if you plug that in, you actually get a 0 in the denominator. So let's look at that algebraically. So the original function was x plus 6 over x squared plus 4x minus 12. Okay. If you were to factor this, let's see what we remember from algebra. This one's not too bad. We'll put an x here and an x here, right? Okay, we have to think of numbers that multiply to get -12, but then add to get +4. So if you're having a good day, you probably think -6 and +2, right? Is that right? And I have a typo, I think. Yeah, my brain. I had a typo in my brain. This says actually x plus 6 there. So I don't know where I got that x plus 2 there. It was really messing me up, though, if you're following along. Okay, and then also you're probably saying, Ms. Brooks, you're falling apart. Okay, let me try this again. If I want a +4 and a -12, how about +6 and -2? Fortunately, when you're doing algebra, when you're factoring with calculus, you kind of know what you want, so you can force it to happen. I wanted that x plus 6 to cancel, so since it wasn't showing up and canceling, I knew that I was having a trouble the momentary lapse in my algebra. If you tried to plug -6 in here, you would get 0 in your denominator, right? So that's what it's telling you. That's why we were getting that hole in our graph, because it gave us 0 in the denominator, which is yucky. Actually gave us 0 over 0, which is not actually as yucky as like 5 over 0, but still it's pretty bad. What we can see now in this factored form is that our x plus 6's will cancel, and that this graph is really very similar to the graph of 1 over x minus 2, right? Now at this point, this graph we can actually plug in -6 into this graph. We couldn't plug it into this graph because it gave us 0 in the denominator. We can plug it into this graph or into this function, and we get 1 over -6 minus 2, which is 1 over -8, or -1/8, which is -0.125. Okay? Which was what our calculator was telling us. And so we just proved it algebraically. Okay, so this is funny. I'm having some retro thoughts here. First of all, when this was in the 90s, the stock market used to always, it didn't used to be, now the stock values are given in decimal. I don't know if you've noticed that. But it used to be in the 90s that it was like 5 7/8 or 5 and 1. They went all the way down to, they did fractions. And so an 8, everybody knew that an 8 was 0.125. That everybody kind of had a sense of, you know how you have a sense of what a half is and what a fourth is, you know, 0.5 and 0.75 and all that. Well, people used to have a much better decimal sense of 8s because the stock market used to report in the 8 to the 8s. But then I guess at some point they're like, no, nobody can fractions, and so they just went to decimal. But it was in my lifetime, maybe not yours. Anyway, that was one retro thing. The other retro thought I had was there used to be this Glade commercial called Plug It In, Plug It In. Do you remember that? Okay. Well, that is the song that you want to do, or you want to remember the first time, or right when you're looking at a limit. The first thing you want to do is plug it in and see if you can't just get the y value by shoving that x value into the function. Remember, the limit is looking for the y value for particular, as you approach a particular x. Sometimes there's a hole and you try to plug it in, you get 0 over 0 or 5 over 0, right? But sometimes you plug it in and it works fine, which is what's going to happen on this homework, which makes this homework really easy. Okay, so for example, yes, is this as easy as what I say? Yes. All you do is take 2 and plug it in for x into this equation, into 4x. So this is just going to be 4 times 2, which is 8. The limit as x approaches 2 of the function 4x is just 8. You know, what is the y value when x is 2? If your function is 4x, well, it's 4 times 2 or 8. Easy. Plug it in, right? On this one, you're going to plug in 1. So you're going to do negative 1 over 3 times 1 minus 1, which is negative 1 over 3 minus 1, or negative 1/2. Easy? All right, fine. Let's do a little trig because that's fun. All right, we'll plug in pi. All right, so that's going to be the cosine of pi over 1 minus pi. Anybody remember the cosine of pi? Good. Negative 1 over 1 minus pi. That is what it is. It's a beautiful irrational number, so we will leave it that way. Okay, so pretty much that's it for this lesson. You do have a little, please remember, and this will, on Wednesday I'll ask you this first thing, how to factor a cubic, and then how to factor maybe a little bit more complicated quadratic. Might want to get some, brush up on factoring. I guess that's what I'm saying. Brush up on it a little bit. See if you can't remember some. You could Google it, or you could, I don't know. I think there are some additional resources in your calculus book you could look up. But if you just Google difference of 2 cubes, or sum of 2 cubes, you'll get the formula for factoring. It's like a minus b, and then a squared minus, I don't know, plus 2ab. I can never remember the difference. I guess I shouldn't advertise that. I always have to look on a sheet somewhere. But maybe we'll put that on resources. Okay, so that's what I would like you to think about for Monday. You can also, for Wednesday, you can also start that first homework assignment. You'll probably be able to knock that one out. It's not so bad. All right?